So welcome back. Let's start. So first of all, I updated a bit the slides that we discussed yesterday, because I may be wrong, but I had the feeling that not everything was crystal clear. Okay, so maybe my feeling was wrong, and I'm glad if that's the case. But I had the feeling that some of the things that I probably taken for more or less granted were not so granted. So, for instance, here when talking about gradient descent, I added a link, okay, to a very good blog post that gives you some intuition about gradient descent. You can. There are also a few things that are maybe too detailed, but I'm confident that you can skip the things you don't care about. But keep in mind that we will talk a bit again gradient descent when we will see neural networks as a way to do prediction. And another thing that I wanted to clarify, but at first I didn't find anything satisfying. So for logistic regression, I already told you that there is this kind of nice visual guide, but I wanted also to find something that explained a bit better how fitting the parameters in logistic regression worked. So after a bit of scraping, I found this nice little video, okay, that has a specific example, a very simple setting, when basically the guy does gradient descent exactly applied to logistic regression. So again, this is not really necessary, okay? We don't care so much about the technicalities of the how, but if you are like me, and like I was when I was a student, basically my brain refused to understand everything that was not 100% clear. So if you are like me, you want to know better, okay, even if it's not strictly necessary. So I should have updated the slides in the website, so maybe check if you download again the PDFs of the slides, you should find these two additional links in the parameter fitting slide of the logistic regression and in the gradient descent slide of the perceptron, okay? There should be no more updates. And today instead, we go on with our browsing of techniques for building machine learning models, especially with a focus on classification. And today we are talking about support vector machines, okay? These are yet another technique. So we have seen, to do a bit of recap, we have seen KNN, which was not really a learning method, but it was the very first naive classification method. Then we have seen linear models, we have seen decision trees, okay, that are, again, quite baseline methods, useful especially because they are white boxes, so they can be easily explained, especially decision trees. And now we are seeing support vector machines, which are, in a way, not so different from linear models in the sense that they strive to find a separating hyperplane for our data points. Okay, so they are not bound to linear separation, as we have seen a main drawback of the perceptron, for instance. But the idea is similar, okay? So obviously the examples are visualized in a two-dimensional space because it's the way paper works, but support vector machines are usually employed in multi-dimensional spaces, okay? That's why we are talking about an hyperplane and not simply a plane. So the core idea is this one. given our data points in a multi-dimensional space, find the hyperplane, okay, in this multi-dimensional space that best separates data points in the requested classes. Supervector machines specifically work with binary classification problems. Okay, they can be extended to multi-class classification. We will see in the slides what are the trivial extensions, but their core functioning is meant to be for binary classification. Okay, so what's novel with respect to, for instance, linear models? Well, first of all, that we want an additional, let's say, constraint in this kind of separating hyperplane, that is maximizing the margin between the data points. Okay, ideally we want to find a separating hyperplane that maximizes this margin. Okay. One reason to do so is that we increase the chance of being able to correctly classifying new data samples, unseen. If we draw the line too close to this set of data points, we increase the risk of misclassifying new data points. Okay, so that is one additional constraint. And the name basically stems from this notion of margin. The data points that are, let's say, at the frontier, that are in a sense the last data points of their kind before moving on to the other kind, they are called the support vectors. Vectors because, as I said, imagine we are in a multi-dimensional space. So each data point is actually described by a vector of attributes. Okay? So this is simply to justify the name. These are the vectors of the data points that support this separating hyperplane. They are the reasons why the separating hyperplane is drawn here. This is just to explain the name. So, this should be more or less clear. A separating hyperplane is defined by a set of parameters. Okay? Imagine that the equation of a plane in a Euclidean space or in a Cartesian space is the same. The only difference is that here we are not bound to 2 or 3 dimensions. So in general, we would like a hyperplane that identifies a region. Okay, when you have an inequality, you identify a region, not simply an hyperplane. That identifies a region, for instance, the positive region above, let's say, the hyperplane, when the class, for instance, is a positive example, and the negative hyperplane if, for instance, the class is a negative example. Okay, so again, you want an hyperplane that separates your data space in 2 regions, and those regions contain different classes. That's what you're saying here. This system of inequalities implies that this inequality always holds, okay? Because if the target is positive, the plane is positive. If the target is negative, the plane is also negative in the negative space. Why do we care about this? Because this is basically the system of equations that you want, the optimization problem, in a sense, that you want to solve to find this separating hyperplane. So this is actually the problem that the specific algorithms behind supervector machines tries to solve. We want to find the maximum separating hyperplane. What does it mean? With the maximum margin. Okay, that's our goal. By solving this optimization problem, we want to maximize the margin based on what? On the coefficients of the hyperplane, so what we call beta, or what perhaps we called weights in the case of the perceptrons. So this is the actual equation that we want to solve, okay? We want to have the highest margin possible. And putting these additional constraints on the coefficient simply serves to have a unique solution, okay, to focus on finding at least one solution. So this is the kind of problem that algorithms implementing the idea of support vector machines want to solve. How can this be solved? Again, we don't care so much about the specific technique. We only mention it. And again, you can expect some reference to go deeper if you want. The basic idea is that, as we said, this is a constrained optimization problem. One of the methods for solving constrained optimization problems is the Lagrangian multiplier method. Okay, so if you know what it is, fine. If you don't know what it is not really necessary, but if you want to know more, here there is another nice explanation. Okay, all of these explanations are meant, they are not usually the first Google result. They are meant to be accessible whatever your background is. Okay, obviously in any of these explanations some background is required. For instance, you may probably need to recall some basic concepts about that you learned in some course about operating research or optimization, but they are meant to be the most accessible as it possible. So this is just to say that this is one method, okay, to solve this problem, which means to find the coefficients that we want. What we call beta in this transformed, okay, equation is this summation. Okay? So, fine, we have a method for it is akin in a sense to do gradient descent, okay? That's the same goal. We have the goal of finding the coefficient of a function. Remember that this is always our goal in learning a prediction model or any kind of machine learning model. We want to approximate to find a function, okay? And usually this means that we need to find the coefficients of this function that has a certain shape. In gradient descent, that's a way to do this, to find this coefficient. Here we are using this method taken from optimization theory. It is just a tool to be used to solve a problem. What I care about is that you understand what the problem is. I need to find an hyperplane that maximizes the distance between the two sets of data points. Obviously, this is an ideal situation. Okay? In this multidimensional space, the data points were perfectly linearly separable in the sense that in this multidimensional space there is an hyperplane that perfectly divides the two sets. It is not always the case, so it is much more common instead to have a so-called hard or strict margin. It is much more common to aim at a soft version of this margin. So try to maximize the margin, but tolerate some misclassification. Okay? It may be impossible to find an hyperplane that separates these kind of things. So what do we do? Do not be scared. This is exactly the same optimization problem that we have formulated before. Okay? Compare these two slides. The only additional term is that since we want to tolerate some violation of the constraints, we add to the formulation what in optimization theory are called slack variables. They are penalties for misclassification. So in this formulation, the problem is the same, but we have an additional set of parameters. we want our hyperplane to respect the margin, but we tolerate some error, basically. Okay? Obviously, this is an hyperparameter. So we want that, for instance, that the sum of all the errors that we tolerate being below a given threshold. This threshold is a form of regularization that we already mentioned in the overview slides. Okay, is a form of shaping the solution to our problem. And this again is an hyperparameter. You have basically no real heuristic, no real sound strategy to choose this parameter. You just try. We already learned that sometimes there is no heuristic. We need to try. So this is a typical hyperparameter that you want to do grid search, that we have already seen, for instance, in the case of KNN, when we wanted to do model selection based on the number of neighbors. This is another typical parameter that you try to tune via grid search by simply trying a few values and see empirically what is working best. Obviously, there is an intuition behind this. Not every hyperparameter has a clear intuition. Here is quite clear. The higher the parameter, the higher the penalty you accept for misclassification. That's it. The lowest the parameter, the lowest the penalty you accept. If you set C to 0, for instance, you accept no misclassification. You fall back to the strict case. Okay, that's quite easy to see. Yeah, that's actually what we said. The hyperparameter that is usually called C controls the regularization, okay? And is connected obviously to overfitting. Why? Large values of C have a smaller margin hyperplane, so they try to classify all examples correctly. Instead, a smaller value of C produce larger margins, okay? And so we accept misclassifications. This is a visualization, okay? Yeah, it's actually the other way around because we subtract the errors. Sorry, so I toggled the actual specification. This must be small to have a larger margin. And again, here you can see what the impact of this regularization term is on the separating hyperplane that you are actually shaping up. We mentioned regularization in the sort of overview slides, so these slides should not surprise you. Regularization is a general technique. It is especially used, for instance, in neural networks, okay, neural network-based methods. And it is simply this general idea of anytime we have a loss function, okay, keep in mind that what is the loss function of an SVM? Basically, it's the contrary of this one, okay? That's a loss function. If you remember in logistic regression, we have seen that a way to do logistic regression is maximum likelihood estimation. In that case, it was the same. You maximize the likelihood. If you take the maximum likelihood as a loss function, you simply put a negative sign in front of it. Okay, so when I talk about loss, or when you find some paper or some explanation in a blog or whatever that should be talking about a loss function, but then suddenly jumps to a maximization problem or stuff like that, keep in mind that probably they are taking for granted that you know that you can always take everything as a loss function to be minimized simply by inverting the sign. Okay, so that's again the case. So the idea of regularization is simply to add to the loss function, whatever loss function you are taking, a penalty. Okay? Usually this penalty, the objective of this penalty may be quite heterogeneous in practice. It depends on what you're trying to do, but Generally, this regularization means that you want small parameters in your solution. Okay, so the parameters that you are trying to learn should be small. So, for instance, an abstract example, but if we want to encourage small parameters, one simple regularization term could be taking the norm of our weights, so the beta coefficients, or the quadratic norm. Okay, just a way to encourage small parameters. So, any loss function can have some sort of regularization term. They are penalties, arbitrary penalties that you add to achieve whatever goal you have in mind. In our case, that is in the case of SVM, the goal of the regularization term is to allow some misclassification. So far, as I said, even if you are in a hyperplane situation, so in a multidimensional situation, the subport machines that we presented are still linearly separating the data points. Okay, you have an hyperplane. You don't have discontinuities, for instance. Obviously, we already seen that this is quite limiting. Okay, it basically killed research in neural networks at the time of the simple perceptron. So there are many practical cases in which we want to use non-linear models, okay? Because, for instance, the relationship between the input and the output, so the features that we are basing our prediction on and the prediction variable target is not linear. So there is no chance, basically, to learn a good classifier, linear classifier, if the relationship, the hidden relationship, the function f that you want to learn is not linear. Well, and here is the example that we've seen with the perceptron. No, in the case of XOR, there is no hope. So, support vector machines, let's say, circumvent this problem, not by changing the way they work. They still find a separating hyperplane, but they make this. They find this solution. If we augment the feature set, so the set of the attributes excluded the target variable, obviously. If you augment the set of attributes we are basing our prediction on with a nonlinear combination of the features, that's a way to fall back to a linear separation problem. If we add to the feature set, so what we usually in the practical examples we call the X part of the dataset, so the independent features, with some nonlinear combination of the original features. So in this example, we are actually doing the XOR of the two coordinates. So we add a column in our dataset, okay? We add a column in our dataset. And in this column, we put a value that is derived as the XOR of the other two features, the only two features we have in this example. We incremented our multidimensional space with one additional dimension. But this makes so that now we can find a separating hyperplane between the features. Okay? So, this technique is called nonlinear feature mapping, and it is particularly used with support vector machines. So, whenever you have a d-dimensional space and you want a nonlinear separation, just create a d plus k dimensional space with k are k combination, nonlinear combination of features. Okay, that's one way to not solve but circumvent the problem. This new feature is an artificial feature, okay? It is not something that has to be meaningful. It's just an artificial feature to let the model, to let the technique work obviously be careful if you have a dataset with 100 features and you try to create another 100 artificial features, well, it may be difficult then to understand, for instance, the feature importance. Okay, something that we get with linear models. The coefficients are the feature importance. Here, if it turns out that the most important feature is a nonlinear combination of n other features, it may be not trivial to understand which one amongst the original feature contributed the most. But this nonlinear feature mapping is a technique especially used in support vector machines to circumvent the linearly separating hyperplane problem. Another way to push support vector machine towards nonlinear separation is to extend support vector machines to what are called kernel machines. Okay? In this case, what we are doing is simply embedding this sort of nonlinear feature mapping in the kind of function we want to learn. Remember that in support vector machine the function is a linear function, okay, with beta parameters as we have seen with linear models. With kernel machines, instead, what we are doing, there is a linear function anyway, but we have another function, okay, that can be whatever. So it can be also a nonlinear function. So that's another way to extend support vector machine towards nonlinear case. Instead of aiming to find a separating hyperplane, which is linear by definition, now we want to find a separating, possibly discontinuous surface, so a nonlinear surface. Okay? It can have folds, it can have any different shape. And in fact, what we are doing basically is not so different from what we were doing here. This nonlinear surface is just a linear classifier applied to a nonlinear transformation of features. The only difference is that this time, with nonlinear mapping, is embedded in the function. Why this extension to support vector machine is called kernel machines? Because obviously a great deal of what you can classify depends on the nonlinear function that you choose. This choice, these functions, are called the kernel of the support vector machine extended in this way. And you can have many kinds of kernels. Here there is a simple example, a polynomial kernel or a Gaussian kernel. It is also usually called a radial kernel. Choose whatever function you want, okay? Of course, it should be nonlinear if you want to go beyond linear separation. So again, these are just examples of kernels that you can use. And we will see, actually in software libraries, obviously, usually you have parameters that let you choose amongst a pre-specified, predefined pool of kernels. This doesn't mean that you can't add your own kernel to any support vector machine based classifier if you want. So again, this is just a technicality. This can be a slide with 10 examples. This is the kind of nonlinear feature mapping that you are embedding in your classification function to be able to classify also nonlinear space. Spaces of data points that are not linearly separate. So either you do nonlinear feature mapping in this way, so you modify the dataset, or you keep the dataset as it is, but you modify the function that you want to learn. You have these two alternatives. Okay. Obviously, we, in some sense, introduced another hyperparameter. The radial the kernel that we are using is, to some extent, a parameter of the model. Different kernels may give different results. It depends on the data. There may be a kernel that separates better some data set and some other. Okay? So, for instance, what we may want to do is to perform a grid search both for the regularization parameter C, okay, which stays still in the case of kernel machines. We are still finding a separating, not hyperplane, but surface, nonlinear surface, and we still want to maximize the margin that all the data points have with respect to this surface. That's the same. So usually when you're using support vector machines in a nonlinear setting, at the very least, you do model selection based on both the regularization hyperparameter and the kernel. That's what you usually do. Keep this in mind. Also, for support vector machines, we can have some problems if the representation of classes is not more or less the same. We already discussed this issue. Real-world datasets are oftentimes imbalanced. For instance, in medicine, it is quite common to have fewer classes where a given patient has some sort of disease. Or if you think about an industrial setting, if you want to do, for instance, predictive maintenance, which is a very active field of applied research, usually we have very few samples of faults. And for the vast majority of your dataset, the machines are operating correctly. So that is a problem that is intrinsic imbalanced. Nothing really special. A solution to imbalanced representation of classes is to simply weight the samples, the data samples, differently. We already had this example, I think yesterday, I think. For instance, one easy approach would be to multiply the representation of a given class by a weight factor in a way that rare classes should count more. If I remember correctly, yesterday we dealt with a classification problem. I think it was about churn. And the churning customers were much more fewer than the non-churning customers, okay? So one way to mitigate that problem is to simply make rare, unique data points have a bigger role in shaping the coefficients of our function. That's usually what you do when you have this kind of imbalanced classes problem. Other approaches, I don't remember if they are mentioned in the slides, so I talk about them now. Other approaches would be to oversample your dataset, so add rows copied from existing data points with the rare classes. That can be problematic, obviously, because you are in some sense altering the data distribution, but that could be a solution. So oversampling the rare classes. I have a dataset, I don't take every line once. The rows of my dataset that correspond to a fewer represented class, I sample them more than once, oversampling. And obviously you can do the opposite. You can undersample the most represented classes. Usually, if you can afford, as usual, which means that if your data sample size doesn't get too little, undersampling is to be preferred, because at least you are not altering your original data. You are simply selecting a smaller sample size based on the whole population. Okay, all is fine. We will see an example of these supervector machines in practice as usual, but we restricted ourselves to a binary prediction problem. Okay, I want to find a separating hyperplane in a linear case, or a separating surface, nonlinear surface in the nonlinear case, but we are still separating our data points into two classes. What if we have a multi-class problem with C greater than 2, strictly greater than 2 classes? Well, you have these two approaches. There is no modification to the support vector machine that actually takes care of this, because by their very definition they find separating surfaces. But you can still use support vector machines in one of these two ways. 1 versus all, 1 versus 1. In 1 versus all, you basically train distinct binary classifiers. You train one binary classifier for each class. Do we have 5 classes? We train 5 different binary classifiers. The positive class is the class we are targeting. The negative class is the set union of all the other classes. That's why it's called 1 versus all. So 5 classes, we end up with 5 models. The positive examples, which means what we are measuring as the true positives, true negatives, are the examples from the class we are targeting with this model. And the negative examples, the false positives, the false negatives, are all the other classes. That's why it's called 1 versus all. Okay? So the new data samples is in the class with the maximum margin. That's how we choose between all of these C predictors. Let's collect all of the predictions and then pick the one with the maximum margin. Reasonable. The other technique, 1 versus 1, sometimes you can find it under the name all pairs, but honestly, at least in my experience, it is less common. It is usually called 1 versus 1. What you do? You train a binary classifier for each pair of classes. Okay, so you end up with more models. Okay, every pair of classes. The positive example is from the class you are targeting, the negative from the other. And the new example, how do you attribute a label to the new example amongst the multiple labels you have? It is the one that has won the largest number of pairwise classifications. So let's say I have 3 classes, class A, B, and C. I train my models, so A versus B, A versus C, B versus C. Okay. And then what I do, if I had to predict a new data point, I ask my predictor A versus B, okay, it's A. I ask my predictor A versus C, okay, it's A. Then I choose A, because it won the maximum number of pairwise comparisons. Okay? Obviously, you can have ties. Even here, you can have ties. You can have multiple classifiers with the same, exact same margin. So you need to find a strategy to resolve ties. And obviously the question will be the same question we asked several times. What is best And the answer is the one we gave, unfortunately, several times. There is no best. They are two reasonable strategies, but none of them is, in general, reasonably better than the other. You can always argue in favor of one or in favor of the other. That's it. So if you want to be sure that you're doing the absolute best you can do to improve your classifier as best as you can do, this could be another model selection hyperparameter to some extent. So I have a multi-class classification problem. I want to try supervector machines. I try both 1 versus all and 1 versus 1, and let's see which of the two gives the best performance metrics, whatever they are. Okay. Again, we have no real heuristic to choose. Can we see an example of this? Of course. Again, using our usual library. After the pause, we will investigate the SONAR dataset, which is about rocks. Yeah, it's a signal processing dataset, yeah. I think you want to distinguish whether a given material is metal or rock based on some radio frequency measure, like signals bouncing off of materials in different way.